Swayam Prabha. Digital India. Educated India.
How do we generalize all of this? This is where I am going to now assume that I am not going to minimize f of x such that G1, there are several equality constraints. X is in Rn. There are m equality constraints and p inequality constraints. There are m equality constraints and p inequality constraints. So, obviously now unfortunately as I said, because I can do only so many things on the two-dimensional thing, I am now going to unify all of these conditions together and give you one set of conditions over here. I will define what is called the Lagrangian, which is a function of x, mu and lambda. This is equal to f of x plus sigma lambda I gi of x, I goes from 1 to m, plus sigma mu j hj of x, where j goes from 1 to p. So, there are m Lagrange multipliers corresponding to the equality constrained optimization problems. There are p Lagrange multipliers which are corresponding to the inequality constraints. So, lambda and mu are Lagrange multipliers. So, what is the first order necessary condition is going to be that minus grad f equal to sigma lambda I grad gi, I goes from 1 to m, so this is my first condition over here. The second condition is that all my equality constraints have to be satisfied and all the inequality constraints have to be satisfied, which means they have to be feasible. I could have some of the inequality constraints could become strict inequalities, but all the equality constraints, all the g's have to be exactly equal to 0. There is no other way. Some of the h could be strictly less than 0, some of them could be equal to 0, but no h can be greater than 0. The third condition is all the Lagrange multipliers corresponding to the inequality constraints, they are greater than or equal to 0. And the fourth constraint is the complementarity condition, which says that mu j hj is equal to 0, j goes from 1 to p. If you look at the strict inequality, the complementarity condition, if h is negative, h is allowed to be negative, g cannot be negative, g has to be exactly equal to 0. If any h out of the p inequality constraints, if any h is negative, then automatically it forces the corresponding Lagrange multiplier mu to be equal to 0. But all the Lagrange multipliers corresponding to the inequality constraints mu, they have to be non-negative. The lambdas could be positive, negative or 0, but the Lagrange multipliers mu corresponding to the inequality constraints have to be strictly non-negative. They have to be non-negative. They could be positive or 0. In addition, the strict complementarity condition says that if some constraint h is strictly less than 0, which means it is inactive, it automatically forces the corresponding Lagrange multiplier mu to be equal to 0. So, these are called the KKT conditions, named after Karush, Kuhn and Tucker, who formally laid down these conditions somewhere in the there is some history behind this, how it was laid down and so on. If you go back, there is in the early 1940s, some of these conditions were properly written down, and these are again first order necessary conditions. Just as in unconstrained optimization we had second order conditions, there are also second order conditions, but in the interest of time I will skip those because we need to I need to finish up a couple of topics. I want to go back to a case of solving linear equations using the theory of constrained optimization. So, what do we know about constrained optimization? It is not enough to set the gradient equal to 0. You need to define the Lagrange multiplier, which is equal to f plus lambda, lambda times summation lambda times g, where lambdas are the Lagrange multipliers corresponding to the equality constraints, plus the summation of the Lagrange multipliers times h, where mu's are the Lagrange multipliers corresponding to the inequality constraints. Now the first order condition is that the negative of the gradient should be a linear combination of the gradients of the equality constraints and the inequality constraints. That is what the first KKT condition says. It says the negative of the gradient of the objective function should be a linear combination of the gradients of the equality constraints and of the inequality constraints. All the points should be feasible, which means the equality constraint should be satisfied exactly, all the g should be equal to 0, all the h should be less than or equal to 0. The Lagrange multiplier, the third condition is that Lagrange multipliers corresponding to the inequality constraints, they are non-negative, all the mu's are non-negative. The fourth condition is the complementarity condition, which says if the inequality constraint is inactive, mu has to be equal to 0. If the constraint is active, h is equal to 0, mu, what is the value mu can take? If h is equal to 0, what value can mu take? It can take any non-negative value. It can take positive or negative, but cannot take 0. That anyway is ruled out from the positive non-negativity condition over here. There is no constraint on the sign of lambdas, which are the Lagrange multipliers corresponding to the equality constraints. The only reason I chose different notations for Lagrange multipliers corresponding to equalities, inequalities, so therefore I can write down these, I can make a distinction for the signs. Now we will go back to one problem again in solving linear equations, where we have Ax equal to b, a rays of size m cross n, and it has there are fewer number of equations and unknowns. When there are exactly as many equations as unknowns, we know it has a solution, determinant of A is not 0. It may or may not have a solution when determinant of A equal to 0. When there are more number of equations and unknowns, more often than not we can be sure that there does not exist an exact solution. So we asked for a least square solutions. We try to find that value, that combination of the columns of A which are closest from B. We solved a geometry problem and try to minimize the distance. Now when there are fewer number of equations, we can again solve another problem, because there are several equations. So there are fewer number of equations and unknowns. So there can be several solutions and infinitely many solutions. Out of all of these solutions, which solution will you choose? So there could be many solutions because there is not as much information as the number of unknowns. So which solution will you choose? There are infinite solutions. So I can ask the same question in terms of geometry. I can say amongst all the solutions which satisfy Ax equal to b, find me that one which has the smallest length of x. I mean, there are infinitely many solutions for Ax equal to b. Amongst all those, you find the one which has the length of x is minimized subject to Ax equal to b. Now this is not very unreasonable, right? Because there are infinitely many solutions. So each of you can come up with one solution. But suppose all of us in this room, I say that at the end of this class, all of us should come up with one solution that we can all agree on. Right? This is something which all of us can agree on. There is some intuition that amongst all the solutions that satisfy Ax equal to b, find me that solution which minimizes the length of x. Now this is not something which is unreasonable in that sense. All of us can at least agree on this. Otherwise each of us would come up with a different solution and we will never be able to come to an end to this class. So let us agree that we have decided to find that solution x which has the smallest length such that Ax equal to b. Now what is the length of a vector? If you recall, it is square root of x transpose x. So minimizing the length of the vector, I will now argue, is minimizing this is equivalent to minimizing, because I don't like to have square roots, right? Whenever we try to take derivatives and so on, we never like to have square roots. We like to have things which look nicer. And what is the length of x square? X transpose x. So I am going to minimize x transpose x. Again, just for purposes of making it nicer, because if you recall I said I don't want the half factor to come later on, I will just put a half over here, it does not matter. I want to minimize x transpose x subject to Ax equal to b, then A is of size m cross n and m is smaller than n in this case. Now if you recall this, this is just an equality constraint optimization problem. We know how to take gradients of quadratic functions, we know how to take gradients of linear functions. The only thing is, what is the necessary condition of optimality for this? I will write down the Lagrangian. In this case, I will just ask you to, in the interest of time, I will not be able to derive it. There are lambda is an right. Remember, if you recall, there are Ax equal to b really represents m equality constraints, and for every equality constraint there is one Lagrange multiplier lambda. So there are m of those. I will put all of those Lagrange multipliers lambda 1, lambda 2, lambda m as a single vector of size m, and then I will just define my Lagrange multiplier Lagrangian as half x transpose x plus lambda transpose Ax minus b, because my condition is the same as Ax equal to b is the same as saying Ax minus b is equal to 0. So I could have written down the Lagrangian for every equality constraint, and those happen to be linear constraints over here, and then I can bring all of them together, and finally it will boil down to the Lagrangian is equal to half x transpose x plus lambda transpose Ax minus b equal to 0. Now what is my first order necessary condition? In this case, my necessary conditions are sufficient, are enough, because of certain constraint. In this case, the first order conditions are both necessary and sufficient for me to solve this. I know that minus grad f should be f is equal to half x transpose x. I know that minus grad f should be equal to lambda times okay. In this case, when I write down the first order necessary conditions, I will be able to write it as if you go back to the sum of the in the first few slides, if you go back to what formula I wrote for derivatives and gradients of quadratic functions and linear functions, I will get this one condition over here. In addition, I need to solve Ax equal to b. Right. Now how do I get the solution of x? From this I will write x is equal to minus A transpose lambda. X plus A transpose lambda equal to 0, so I will let x equal to minus A transpose lambda, and then I will put x over here. So I will write A into minus A transpose lambda is equal to b, because x I have written as minus A transpose lambda. Therefore I will get minus of A transpose lambda is equal to b. This means x is equal lambda is equal to, if I can invert A transpose, lambda is this, and x finally I will be able to write it as so. This is just very simple algebra. I know I am rushing through this, but you can go back and verify all of these steps. This is the first order necessary condition, x plus A transpose lambda equal to 0, and I have the equality constraints have to be satisfied. Ax equal to b, I can put x in terms of lambda, get lambda, and finally get x. So this is slightly different from the least square solution that we got. What is the least square solution? X equal to A transpose A inverse A transpose b, and we use that when we had more number of equations. When we have less number of equations, we use x equal to A transpose inverse b. And when we have as many number of equations as unknowns, both of these formulae will be the same when A is invertible. When A is invertible, both of these formulae will end up becoming the same. So now, how do we bring all of these things together in one slide? Right? There is more equations, less equations, equal number of equations. Is there one single formula that encompasses all of these cases? So the way we do that is, remember I said there is we looked at two factorizations of the matrix A. We factorized for a square matrix, we factorized it as LU. We also factorize it as QR when to make the columns of A when they are not perpendicular. We try to find perpendicular columns which have equal length, which we put it in the QR factorization. Now, when A is of arbitrary size, rectangular matrix M cross N, when A is of arbitrary size M cross N, there is a factorization called the singular value decomposition, SVD. Now, this you can factorize as U sigma. This I can factorize as there is a 2 over 2 has to be okay. I can factorize any M by N matrix. It could be rectangular, it could be square, it could have more number of equations, less number of rows. I can factorize it as U sigma V transpose, where U, the columns of U contain the eigenvectors of AA transpose. The columns of V contain the eigenvectors of A. Now, let me go repeat. A can be factorized as U times sigma times V transpose. The columns of U contain the eigenvectors of AA transpose. The columns of V contain the eigenvectors of A transpose A. Sigma contains, sigma is U is a square matrix of size M cross M. V is a square matrix of size N cross N. Sigma, capital sigma over here, is a rectangular matrix of size M cross N. It contains the square root of the non-zero eigenvalues of AA transpose or of A transpose A. Now, you can do the square root business because we can show that the eigenvalues of AA transpose or A transpose A, they are non-negative. Because A transpose A or A transpose, they are positive semi-definite matrices. Therefore, the eigenvalues are non-negative. Therefore, you can take the square root and the square root is well defined. You will never have a problem of getting complex numbers. So, all the numbers in capital sigma are real numbers, which is not a problem. They are square root of the non-zero eigenvalues of AA transpose or A transpose A. So, how does it look like? When M is greater than N, sigma is a tall matrix. It has more number of rows than columns. When M is smaller than N, sigma is a fat matrix. It has more rows than the number of columns, and these are the sigma 1, sigma 2, sigma 3 and so on. In this case, I have given it to you for a very simple illustration. They are the square root of the non-zero eigenvalues of A transpose or A transpose A. Now, A hash, this is called the pseudo inverse. This is called A dagger, is called the pseudo inverse. It is defined as V sigma pseudo inverse U transpose. A dagger is V sigma pseudo inverse U transpose. Now, the advantage of doing this is when you have Ax equal to B, if there are uniques, if A is inverted, I will write, there are several cases which we have considered, right? Equal number of equations, more number of equations, less number of equations. All of those I can conveniently encompass and write X is A pseudo inverse B. And depending on the particular case, it will choose it accordingly. If there are equal number of equations and unknowns, then, and if A is invertible, the pseudo inverse will become the inverse of the matrix. If you have more number of equations than unknowns and the columns of A are independent, then it will result in the least square solution. If there are less number of equations and unknowns, it will come to the solution that we wrote in the previous case, which was the smallest norm solution, the smallest size solution amongst all the solutions which satisfy Ax equal to B. So, this singular value decomposition allows me to give you a concise representation of all the different cases of Ax equal to B, equal number of equations and unknowns, more number of equations and unknowns, less number of equations and unknowns, A invertible, A non-invertible, all of it is taken care of in this case, where A dagger is the pseudo inverse of A. I define a pseudo inverse because rectangular matrix will not have an inverse. Likewise, there are square matrices which are not invertible. So, for those we have pseudo inverses. So, it is called a pseudo inverse because it behaves like an inverse in some very restricted conditions. Of course, A does not have an inverse under several conditions. Like I said, when it is a rectangular matrix, it does not have an inverse. When the determinant of A is equal to 0 and A is a square matrix, it does not have an inverse. So, you can only define what is called a pseudo inverse over here. So, pretty much linear algebra, whatever we have done so far with a little bit of optimization thrown in, has allowed us to answer some of these questions that we started off earlier on, right? When do systems of equations have solutions? if there are things which are changing over time, how fast do they grow? Those are captured by the eigenvalues. And the eigenvectors are certain preferred directions, which also we saw those. Then if you either have more number of variables than unknowns or less number of variables than unknowns, now how do you find at least one solution which in some sense has some geometric interpretation? There are more number of equations, we try to find the closest norm solution, or we try to find the smallest error solution. We try to make the B vector as close as possible to the columns of A. If there are more number of variables and unknowns, we said amongst all the solutions, let us try to find the one which has the smallest length. And that is how in both of these cases, optimization was useful to enable us to come up with solution, at least linear algebraic ways of doing this. Each of these has statistical interpretations, which will be covered, as I said, in the model building, machine learning, or statistics parts, or regression parts by some of our colleagues. But all of them will finally, in several cases, be able to come up with conditions such as summarizing all of these different situations can be summarized as X is Ax equal to B when A is an arbitrary matrix of size m cross n. I have made no claims about whether it's a square matrix, whether the columns are independent or the rows are independent. X I can write as A pseudo inverse times B. And finally, the cheat sheet that I promised you, when A is square. So this is when there are two cases which are possible. In the first case, if A is invertible, so this is so on the left hand side, they are all equivalent characterizations of non-singular matrices. So non-singular matrix A is invertible, it is a square matrix, columns are independent, the rows are independent, the determinant is not 0, Ax equal to 0 as a unique solution, the 0 solution, Ax equal to B as a unique solution for any B, A has full rank, the row rank is equal to column rank, the number of independent rows is equal to n, the number of independent columns is equal to n, therefore the columns span entire n-dimensional space, the rows span the entire n-dimensional space, all the eigenvalues are non-zero, A transpose A has positive definite, and A has n positive singular values. The singular values are those which go into the matrix sigma that we said in the previous case. Now A is singular, it is equivalent to saying A is non-invertible, some columns are dependent, some rows are also dependent, the determinant is exactly equal to 0, Ax equal to 0 has infinitely many solutions, Ax equal to B may or may not have solutions, it all depends on B. If B can be written as a combination of the columns of A, it has infinitely many solutions. If the determinant of A is equal to 0, which is what the right hand side case we are doing, if the B cannot be written as a combination of columns of A, it has no solution. Oh. I'm sorry, A is rank less than n, the columns do not span Rn, the rows do not span Rn, 0 is one of the eigenvalue. A transpose A is only positive semi-definite, it is not positive definite, and it has R, which is strictly smaller than n, positive singular values. So this is the final summary or cheat sheet that I promised you about when A is a square matrix. So with this I will conclude.